The Sun, in the language of orbital mechanics, is not a destination. The Sun is a hole, and every planet in the solar system sits at a different depth inside that hole, which means reaching any of them is a different kind of falling. Some planets pull you in too fast for any rocket to stop. Some let you coast almost free, then ask for something you did not expect to give. Some demand a journey longer than the careers of the people who built the spacecraft. And some can only be reached if you agree, before you leave, that you will never be able to stop when you arrive. The planet you would assume is easiest to reach turns out to be one of the hardest. The planet 10 times farther away turns out to be one of the easiest. The map you carry in your head of which worlds are close and which are far has almost nothing to do with how hard it is to actually go there. Get cozy. Hit subscribe if you haven't yet, because by the end of this, the word close will mean something entirely different every time you hear it about another world. Now, let's gently fall into this. Part 1. The closest planet you cannot reach. There is a map of the solar system that most of us learned as children. The Sun is in the middle, and around it, in tidy concentric rings, the planets are arranged in order. Mercury closest, then Venus, then Earth, then Mars, then the great empty stretch out to Jupiter, and beyond that, Saturn, Uranus, Neptune, and at the far edge, in the version many of us first learned, Pluto. The order of the planets is one of the first lists of the universe a person is ever asked to memorize, and the implication of that list is almost too quiet to notice. The implication is that closeness equals familiarity. The implication is that the planet next door must be the planet we know best, and the implication is that if a planet is hard to reach, it must be hard to reach because it is far away. That is the assumption this story is going to take apart, slowly, carefully, and one planet at a time. Here is a fact that, the first time you hear it, sounds like a typo. The closest planet to Earth is not Mars. The closest planet to Earth is Venus. On average, the distance from Earth to Venus at its closest is around 25 million miles, or about 40 million kilometers, which makes Venus, on the scale of planetary neighborhoods, the next-door house. The planet that is most often described as Earth's twin in habitability arguments and science fiction novels is Mars. But Mars is not the second closest planet to us. Mars is third. The second closest planet to Earth is Mercury. At its closest approach, Earth and Mercury are separated by about 48 million miles, or about 77.2 million kilometers. Mars, by comparison, sits on average around 55 million miles away, or about 88.5 million kilometers. And only every 26 months does the relative geometry of the two planets bring them as close as 36 million miles, or 59 million kilometers, and only for a few weeks at a time. So in the average accounting, the order of nearness from Earth is Venus, Mercury, Mars. The order most of us carry in our heads is Venus, Mars, Mercury. The map of the solar system you memorized in elementary school is, in this particular small way, lying about how the inner planets are arranged in relation to where we are. But that small lie is the entry point into a much bigger one. When humans began sending spacecraft to other planets in the early 1960s, the order in which we visited them was not the order of their nearness. The first planet we touched with a spacecraft was Venus, in 1962, by way of NASA's Mariner 2, then Mars in 1965, by Mariner 4, then Jupiter in 1973, by Pioneer 10. Each of those visits represents an enormous engineering achievement, but you can already see the strangeness in the timing. Jupiter, the largest planet in the solar system and the fifth out from the Sun, was visited a full 9 years before the closest planet we hadn't yet touched. And Mercury, the second closest planet to Earth, the one our map says should be the most accessible after Venus was not visited until 1974 by Mariner 10, more than a decade into the planetary exploration era. That is the first strangeness, and there is more. Mariner 10 flew past Mercury 3 times in 1974 and 1975. 3 flybys. Not 3 orbits, not 3 landings, 3 glancing passes by the planet, during which the spacecraft and the planet briefly occupied the same neighborhood. And Mariner 10 took pictures and made measurements, and then continued on its way. Over those 3 flybys, Mariner 10 managed to map 40% of Mercury's surface. 40%. The other 60% stayed unmapped, in shadow, in mystery, for decades. And then, for 30 years, nothing. For 30 years, while we orbited Venus, while we placed rovers on Mars, while we sent Pioneer 11 and Voyager 1 and Voyager 2 and Galileo and Cassini and Ulysses and New Horizons across the outer solar system and into interstellar space, while we built telescopes the size of buses and pointed them at distant galaxies, we did not send a single spacecraft to the planet that, by the simple geometry of the solar system, was the next closest world after Venus. Not because we didn't want to, not because we didn't have the rockets, not because we weren't curious. Mercury sat in our sky every dawn and every dusk, our second closest neighbor, with 40% of its face known and 60% of it unknown, and we left it alone. You can feel the question forming. Why? Why would the planet next door be the planet we ignore? Why would something that close to us be the thing that we, the species that strung probes across the entire solar system, simply walked past for 30 years? The answer is that the planet we call closest, in the language of maps and the language of straight-line distance, is not closest at all in the language that actually matters. The language that actually matters is the language of orbital mechanics. And in that language, the word close is doing a kind of work most of us have never had to think about. Close in maps means short distance. Close in orbital mechanics means matched velocity, manageable delta V, and a trajectory the math will allow. 2 of those 3 things can fail to be true at the same time that the first one is screamingly, obviously, sitting right next to you true. Mercury is close in the first sense and astoundingly far in the second. The thing the early childhood map left out is that the solar system is not a flat board with planets pinned to it. The solar system is a vast, rotating, gravitationally complex object in which every planet is moving very fast, in different directions, around a very heavy thing at the center. Reaching another planet does not mean walking toward it in a straight line. It means matching its motion. And the closer a planet sits to the Sun, the deeper into the Sun's gravitational pull it lives, and the more the act of reaching it becomes an act of falling into a hole rather than crossing an empty room. We will spend the next few minutes inside that idea, because it is the central reframe of this entire video. You will not understand why each of the planets resists us in a different way until you have felt, in your body, what it means for a destination to also be a whole. Stay with me, because by the end of this part of the story, the question is going to flip. We are going to stop asking why Mercury is so hard to reach. We are going to start asking why we ever assumed, in the first place, that any planet was reachable at all. Part 2. Mariner 10, and then 30 years of silence. To understand the 30-year silence, you have to understand the noise it sat inside. The decade leading up to 1974 was not a quiet decade in space exploration. The Apollo program had just sent 12 people to the surface of the Moon and brought them back. Mariner 2 had reached Venus, Mariner 4 had reached Mars, Pioneer 10 had reached Jupiter, Skylab was overhead. The Soviet Union was placing landers on Venus and watching them broadcast briefly from the surface before the heat and the pressure crushed them. The world was awash in pictures of other worlds, and the rate at which those pictures were arriving was accelerating year by year. Then Mariner 10 arrived at Mercury in 3 brief passes, and the rate of pictures from that one specific planet just stopped. Mariner 10 was a remarkable spacecraft on its own terms. It was launched on November 3rd, 1973, and it carried something nobody had carried before, a deliberately designed plan to use the gravity of one planet to bend the spacecraft's path toward another. The plan was to fly past Venus, let Venus's gravity reshape the trajectory, and arrive at Mercury for a flyby. And then, because the orbits of the spacecraft and the planet would line up again half a Mercury year later, Mariner 10 was going to come back and do it again. And then a third time, 3 flybys of the planet closest to the Sun by a single small probe powered by solar panels in less than a year. It was, for 1973, a feat of trajectory design so audacious that it had its own name in the technical literature, a Venus-Mercury swing-by mission. It was the demonstration, the proof of concept, that gravity assists could be used to reach destinations that brute force rocket science could not afford. Mariner 10 arrived at Mercury for the first time on March 29, 1974. It came within about 700 kilometers of the surface. It took thousands of photographs. It mapped craters and basins and ridges that had never been seen by human eyes. It measured a faint but real magnetic field around the planet, which surprised everyone because a small, slow-rotating, allegedly long-dead world was not supposed to have a magnetic field at all. It detected a tenuous atmosphere, almost a vacuum but not quite, and it measured surface temperatures swinging from negative 170 degrees Celsius on the night side to over 420 degrees Celsius on the day side. It came back 6 months later, in September of that same year, and saw more. And then a third time, in March of 1975, before its attitude control fuel ran out and its mission ended. By the time Mariner 10 died, it had mapped roughly 40% of Mercury's surface. The other roughly 60% had been pointing the wrong way each time the spacecraft flew past, and Mariner 10 could not stop, turn around, and look at it. It was a flyby probe. It was always going to leave. And then, for 30 years, nobody went back. You have to feel how strange this is, because it is the kind of strangeness that hides in plain sight inside a list of dates. While Mercury was being ignored, NASA and the Soviet space program, and later ESA and JAXA, sent dozens of spacecraft to other planets. Venera 9 and Venera 10 landed on Venus in 1975 and broadcast pictures from the surface. Viking 1 and Viking 2 landed on Mars in 1976 and ran for years. Voyager 1 and Voyager 2 launched in 1977 and flew past Jupiter, then Saturn, and Voyager 2 went on to Uranus in 1986 and Neptune in 1989. Galileo orbited Jupiter from 1995 to 2003. Cassini orbited Saturn from 2004 to 2017. New Horizons launched in 2006 and reached Pluto in 2015. Hayabusa reached an asteroid and brought a sample home. Stardust brought home a piece of a comet. Rosetta landed on a comet. Mercury was not visited again until March 11, 2011, when Messenger finally entered orbit. 37 years after Mariner 10's first flyby. The first reaction most people have, when they hear this gap stated this baldly, is to look for an obvious explanation. Maybe Mariner 10 saw everything there was to see, but it didn't. It saw 40%. Maybe the place was just boring, but it wasn't. Mariner 10 had already detected a magnetic field nobody had expected, and an atmosphere nobody had expected, and craters more numerous than the Moon's, and surface features that defied easy interpretation, and a planet that had clearly cooled too fast, geologically speaking, to look the way it looked. Maybe NASA wasn't interested, but they were. Mission proposals to revisit Mercury were drafted, presented, and seriously considered throughout the late 70s and the entire 1980s. Maybe the budget wasn't there. The budget was tight, but the budget was tight for everything in the post-Apollo decades, and the outer planet missions that were dramatically more expensive somehow found their way through anyway. None of the surface explanations actually explain a 30-year gap on the second closest planet to Earth. There is one explanation, and only one, and it is the one nobody ever told you in the elementary school version of the solar system map. The math of getting to Mercury, with the rockets we had, was not just hard, the math was barely possible at all. This is the part of the story that bends most listeners' intuitions out of shape, and it deserves to be told slowly. The thing that makes Mercury hard to reach is not its distance. The thing that makes Mercury hard to reach is the Sun. And the Sun makes Mercury hard to reach in a way that goes against almost every instinct a person has about what it means for a destination to be close. Hold that thought. We will spend the next chapter inside it. And by the end of that chapter, you are going to understand something that no map you have ever seen of the solar system has ever told you, which is that the Sun is not the bright thing in the middle of the diagram. The Sun is a hole, and to reach the planet next to it, you have to learn how to fall slowly. Part 3. The Sun's Gravity Well. Imagine, for a moment, that you are not a probe. You are not a spacecraft. You are a small thing in orbit around the Sun, currently riding along with the Earth. You have been doing this your entire life, the way every object on Earth's surface has been doing it from the moment it formed. The Earth is moving around the Sun at roughly 30 kilometers per second, which is to say 90 times the speed of sound. Everything on Earth, including you, is also moving at 30 kilometers per second around the Sun. We do not feel it. We do not feel any of it. The Earth's atmosphere moves with us. The buildings move with us. The trees move with us. The seas move with us. And our inner ears, which evolved to detect changes in velocity rather than steady-state velocity, simply do not register the fact that we are flying around a star at extraordinary speed. Now, imagine that you decide you want to fall toward the Sun. You want to drop in gently and land on the planet closest to it. You picture this in your head, the way you would picture dropping a stone down a deep well, a clean, neat, vertical descent. The thing your imagination is leaving out is the 30 kilometers per second that you already have. You cannot fall toward the Sun. The Sun is not below you, it is over there, and you are sailing past it sideways at the kind of speed that, if you forgot to keep doing it, would already be unimaginable. To actually fall toward the Sun, you have to first stop the sideways motion, or at least you have to stop most of it. Otherwise, you do not fall in. You just keep going around, the way Earth keeps going around, the way every other planet keeps going around, the way the entire solar system keeps going around. You are in orbit. Orbit is what happens when you fall toward a thing and miss it sideways forever. To actually arrive somewhere closer to the Sun, you have to undo the missing. Undoing the missing is not free. Now, picture what happens once you do begin to fall inward. The Sun's gravity is staggeringly strong. The closer you get, the harder the Sun pulls. The harder the Sun pulls, the faster you accelerate. By the time you are anywhere near Mercury's orbit, the Sun has accelerated you to speeds that are wildly faster than the speed at which Mercury itself orbits. You arrive at Mercury's neighborhood not as a slowly descending visitor, but as something close to a hypersonic projectile, fired by the Sun's gravity well, that is now going to scream past Mercury at relative speeds the planet has no chance of catching. This is the actual physical situation for any spacecraft trying to reach Mercury directly. You cannot just point the rocket at the planet and let go. If you do that, the Sun's pull turns the journey into freefall, and by the time you arrive, You are going so fast relative to Mercury that you would need an enormous amount of fuel to stop. So enormous, in fact, that the fuel required to stop would have been larger than any rocket built in the 1970s could carry to the inner solar system in the first place. The fuel required to stop turns out to be larger than the fuel required to leave Earth. That is the sentence that sat at the bottom of NASA's Mercury problem for 30 years. The fuel required to stop at Mercury, if you go directly, is larger than the fuel required to leave Earth, and nobody in the world had a rocket that could carry that much fuel. There is a way to think about the geometry of this that might help. The solar system is sometimes drawn as a flat disk with the sun at the center. That picture is correct as far as it goes, but it is also misleading because the sun in that picture looks like a regular object sitting on the same flat surface as the planets. A better picture is the one physicists draw for gravity wells. In that picture, you take the flat disk and you bend it downward at the center, like a thin rubber sheet with a bowling ball sitting on it. The bowling ball is the sun. The bend in the sheet is the sun's gravity. And the planets are not all sitting on a flat surface. The planets are sitting at different heights on the curved sheet, with the inner planets perched on the steep inner slope of the well, and the outer planets resting comfortably on the gentle outer rim. In this picture, Earth is sitting partway down the slope. Venus is a little deeper. Mercury is further down still, almost at the bottom of the steep inner slope. Saturn is way out on the flat part of the rim. Pluto is so far out the slope is almost imperceptible at that distance. Now ask yourself, which direction is uphill? The intuition almost everyone has, until they encounter this picture, is that uphill means farther from the sun. Uphill, you think, must be the direction you have to work to go. So reaching Saturn, in this picture, would be uphill. You have to climb out of Earth's groove and roll your way to the gentle slope at the rim. But that is not the right picture for what fuel does. To reach the outer planets, you do have to spend energy to climb out of Earth's groove. But once you are out, once you are loose, the gentle outer rim of the gravity well does not demand much more of you. You can coast along it slowly, almost in a straight line, and arrive at Saturn with a relatively modest amount of additional energy. The whole journey, in trajectory design terms, is the same kind of energy expenditure as launching to Earth orbit in the first place. We will come back to this in later chapters, but it is the reason Jupiter, which is much farther than Mercury, requires roughly the same energy to reach. To reach the inner planets, the picture is different in a way that defies the everyday meaning of uphill. To reach Mercury, you have to go downhill, and going downhill on a steep gravity slope means accelerating, not slowing. You have to actively brake against gravity to keep yourself from arriving at the bottom of the well at a speed nothing can stop. The deeper into the sun's well you intend to go, the more delta V you need to spend not on going down, but on not falling. Imagine you are at the top of a roller coaster track and you want to stop halfway down. You don't get there by letting go. You get there by gripping the brake the entire way. The sun's gravity well is a roller coaster with no brake built in. The only brake is the fuel the spacecraft carries. And every kilogram of fuel you carry is also a kilogram of payload you couldn't carry, a kilogram of instruments you couldn't bring, a kilogram of margin you couldn't keep for any of the things that go wrong over a multi-year mission. This is why, for 30 years, Mercury was unreachable. Not because nobody wanted to go, not because the planet was uninteresting, not because the engineering was beyond imagination, but because every direct trajectory required carrying more fuel than any rocket of the era could lift to the inner solar system, and every clever alternative had not yet been invented. The sun's gravity well was the wall, and every probe that imagined climbing down it ran into the same answer: too fast, too soon, too much fuel, too little payload, not possible. Hold this idea, because it is going to come back. The phrase, the one you are going to hear again later, the one that this entire video is built around, is this: close is not easy. Mercury is close in distance and astoundingly far in delta V. The Sun made the planet next door into the planet we could not reach. And every reach for any other planet from now on, every Mars architecture, every Jupiter mission, every Saturn flyby, every Uranus deferral, every Pluto cancellation is going to turn on a different number than the one in our childhood maps. Distance, by itself, has very little to do with how hard a planet is to reach. The variables that actually matter, delta V, fuel mass, radiation, sunlight, communications, time, are the ones we are going to spend the rest of this story uncovering. The Sun's gravity well is the first one. There are 7 more. But before we leave the Sun's well, before we move out from Mercury and follow the slope outward to the rest of the solar system, there is one more thing to say. The thing that makes Mercury hard to reach is, in a quiet way, the same thing that makes Mercury possible to reach at all. Because if you cannot use brute force to break against the Sun's pull, you have to use something else. You have to use the planets themselves. You have to fall toward Mercury so slowly, by such a circuitous, looping, multi-year route, that by the time you arrive, you are barely moving relative to it. Nobody knew how to do this until 1985, when one person at the Jet Propulsion Laboratory sat down with the orbital equations and found a route nobody had seen before. We will spend the next chapter with her. Part 4. Chen Wanyan finds the route. The Jet Propulsion Laboratory sits in the foothills of Pasadena, California, surrounded by the kind of dry, sloped, semi-arid landscape that has been the home of American spaceflight since the 1940s. It is a working laboratory, an engineering campus, a place where the practical problem of how to make a small object go very far and arrive in a useful condition is solved every day in offices that look very much like ordinary office buildings. By the early 1980s, JPL was the place in the world that built outer planet spacecraft. Voyager 1 and Voyager 2 were JPL spacecraft. Viking was a JPL mission. Galileo, then in development, was a JPL mission. JPL knew, by then, how to design trajectories for missions to almost anywhere in the solar system, except Mercury. In 1985, a JPL trajectory designer named Chen Wanyan was working on the problem. Chen Wanyan had been trained at the Massachusetts Institute of Technology in nuclear physics, and she had brought to JPL the kind of intuition for the deep machinery of orbital mechanics that, in retrospect, is the only kind of intuition that solves problems like the one she was about to solve. She had been thinking about Mercury for years. Her colleagues had been thinking about Mercury for years. NASA had been thinking about Mercury for years. And the answer, every time, had been some version of, not with the fuel we have, and not with the rockets we have, and not in any timeline we can afford. The standard approach had been to chase Mercury directly, launch toward the inner solar system, let the Sun pull the spacecraft in, and burn most of the fuel on board braking at the end, so that the spacecraft could enter Mercury orbit instead of screaming past it. This was the kind of approach that worked, sort of, for the closer planets. Mars missions did something like this, and so had Mariner 10 on its way to Venus. But Mercury is deeper into the Sun's gravity well than Venus, and the braking burns scaled in a way that nobody could finance. By the time you accounted for the necessary fuel, the spacecraft itself had to be tiny, and the rocket had to be enormous, and even then, the margins were so thin that any small failure during the long cruise would kill the mission. Chen Wanyan began to think about the problem from the other direction. Instead of fighting the Sun's pull, what if you used it? Instead of one mission to Mercury, what if you turned the trip into a series of gentle encounters with the inner planets, each one bleeding off a little speed, until the spacecraft was, finally, slow enough relative to Mercury for a normal-sized rocket motor to slot it into orbit. The idea was not entirely new. Gravity assists had been used since Mariner 10 itself. The principle is straightforward to state and surprisingly counterintuitive to feel. When a spacecraft flies past a planet, it briefly enters the planet's gravitational influence. The spacecraft does not steal energy from the planet, but it does swap momentum with it. From the planet's perspective, the spacecraft arrives, swings around, and leaves at the same speed it came in. From the Sun's perspective, from the heliocentric frame, which is what matters for moving around the solar system, the spacecraft has, depending on the geometry, picked up or shed velocity. You can use a flyby to accelerate, and you can use a flyby to brake. Voyager 2 used gravity assists to accelerate past Jupiter and Saturn and out to Uranus and Neptune. The same trick played in reverse, playing the planet against the spacecraft. Instead of 4, it could be used to slow down. Chen Wanyen's insight was that you could chain these encounters. Not one gravity assist, not 2, a whole sequence. A trajectory that, instead of going to Mercury, went around the Sun and around the Sun and around the Sun, picking up small braking encounters with Earth, Venus, and Mercury itself again and again over the course of years. Each encounter would shed a little of the spacecraft's heliocentric velocity. Each encounter would bring the spacecraft's speed closer to Mercury's speed. By the time the spacecraft had done about 15 loops around the Sun, the speed difference between the spacecraft and Mercury would be small enough that a small rocket burn could capture the probe into Mercury orbit. The trajectory she designed flew past Earth once, past Venus twice, past Mercury 3 times. 6 gravity assist encounters in total. The journey would take about 6.5 years from launch to Mercury orbital insertion. It would cover an enormous total distance, billions of miles, far more than the simple straight-line distance from Earth to Mercury would suggest. But the fuel requirement, at the end, would be small enough that a spacecraft of modest size, launched by a rocket that already existed, could carry it. Pause inside this for a second, because it is one of those quiet moments in the history of science where the universe relented on a 30-year problem because one person sat down and looked at the problem differently. There was no new rocket. There was no new propellant. There was no breakthrough technology that suddenly made Mercury reachable. There was a route, and the route had always been there, hidden inside the equations of orbital mechanics, waiting for someone patient enough to find it. Chen Wanyen found it. The route had a strange quality. To reach a planet only 48 million miles away, at its closest, the spacecraft would travel a path several billion miles long. To save fuel, the spacecraft would spend years going the long way. To brake, the spacecraft would never fire its main brake. Until the very end, it would let the planets themselves do the braking, through encounter after encounter, year after year. The whole architecture of the mission was patience. When she presented the idea, the reaction at JPL and at NASA was a mixture of relief and skepticism. The math worked. The trajectory was real. The spacecraft could be built. But it asked NASA and its partners to commit to a mission that would not arrive at its destination for more than half a decade after launch, and not begin its main scientific work until a full decade had passed. The kinds of programmatic commitments that ask a space agency to plan a decade out are commitments that institutions resist because the personnel turnover, the budgets shift, the political weather changes. Yet the route was the only route. Anyone who wanted to reach Mercury, anyone at all, was going to have to walk this slow, long path. Chen Wanyen had shown, with mathematical certainty, that no shorter path was going to work. So the proposal sat. It sat for the rest of the 1980s. It sat through the early 1990s. NASA studied it, refined it, packaged it, repackaged it, considered it for various mission lines, deferred it for budgetary reasons, brought it back when budgetary reasons changed, deferred it again. The trajectory existed. The spacecraft existed in concept. The mission did not exist as a funded thing. Then, in the late 1990s, NASA created a new program called Discovery. The Discovery program was designed to fund relatively small, focused planetary missions on relatively tight budgets, not flagship-class missions like Galileo or Cassini, but more modest investigations. A Mercury mission was selected. The mission, eventually, would be called MESSENGER, an acronym for Mercury Surface, Space Environment, Geochemistry and Ranging. It would be a small spacecraft, only a little over a ton at launch, including all of its fuel. It would carry a sunshade against the heat. It would carry a suite of instruments to map the planet, measure its magnetic field, sniff its atmosphere, and chart its chemistry. And it would fly Chen-1-yen's route, the one she had found in 1985. It is worth saying, gently, that the discoveries of one trajectory designer at one laboratory do not always come with parades. Chen-1-yen's name is not a household name. The route she found is not in the public imagination the way Voyager's Grand Tour is. But every single image of Mercury you will ever see, every measurement of Mercury's polar ice, every map of Mercury's surface, all of that exists because she sat down with the equations and found the only path that worked. The route is the only route, and it was found not by an institution, not by an army of engineers, but by one person doing one piece of patient mathematical work in one office in 1985. Think for a second about what that means for every other planet we have not yet reached. Each of them, somewhere, has a Chen-1-yen route waiting to be found. Some of those routes have been found. Some of them have not been found yet. Some of them may not exist with the tools we currently have. But the cleverness, the patient looking at the math from a different angle, is the thing that turns a 30-year impossible into a 6-year possible. It is the thing that turns "we can't reach Mercury" into a launch in 2004. The phrase to remember, the one that is going to come back later in this story when we talk about Pluto, is this: the route is the only route. The universe does not give us many ways to reach the places we want to go. Sometimes there is one. Sometimes there is zero. The discipline of planetary exploration is the discipline of finding the routes that exist and accepting that we cannot reach places where no route does. Messenger launched on August 3rd, 2004. The journey to Mercury orbit would take just under 7 years. Part 5. Messenger, 7 years, 4.9 billion miles. The Delta II rocket lifted off from Cape Canaveral at 5:15 in the morning, local time, on August 3rd, 2004, carrying Messenger on top of it. The spacecraft was small by interplanetary standards. It was 1.3 meters wide and weighed just over 1 ton, including all of its fuel. Most of that ton was fuel. The instrument payload, the cameras, the spectrometers, the magnetometer, the laser altimeter, was a small fraction of the spacecraft's mass. The largest single structural element was the sunshade, a ceramic fabric panel about 10 feet by 8 feet, attached to the side of the spacecraft that would face the sun for the entire mission. The sunshade was simple, but it was the single piece of engineering that made the mission possible. Behind the sunshade, the temperature would stay near room temperature. In front of the sunshade, the temperature would reach hundreds of degrees Celsius. The spacecraft was going to spend the better part of a decade carefully, constantly, autonomously, keeping its sunshade pointed at the sun while the rest of it did its work. The Delta II reached escape velocity, separated, and sent Messenger on its long arc into the inner solar system. The probe began the first of its many loops around the sun. The numbers of the journey are the kind of numbers that sound, at first, like science fiction. The total path length, from launch to Mercury orbital insertion, would be approximately 4.9 billion miles, or about 7.885 billion kilometers. For comparison, that is more than 50 times the distance from Earth to the Sun. It is more than the entire distance from Earth to Jupiter. To reach a planet whose closest approach to Earth is only 48 million miles, Messenger would travel a distance that, drawn as a straight line, would take it past Saturn. The route was not a straight line. The route was a series of slowly tightening loops around the Sun, each loop intersecting one of the inner planets at exactly the right moment to bleed off velocity. The first encounter was with Earth itself. On August 2nd, 2005, almost exactly 1 year after launch, Messenger came back past Earth at a closest approach of about 2,300 kilometers. The flyby reshaped the spacecraft's heliocentric orbit, slowed its outward arc, and aimed it at Venus. Then Venus, twice. On October 24th, 2006, Messenger passed Venus the first time. The flyby was at a distance of about 2,900 kilometers from Venus's surface. Then again, on June 5th, 2007, Messenger returned to Venus and made a much closer approach, about 338 kilometers above the cloud tops. Each Venus encounter reshaped the trajectory further. Each one shed velocity. Each one brought the spacecraft's orbit a little closer to Mercury's. Then Mercury 3 times. On January 14th, 2008, Messenger made its first Mercury flyby, passing about 200 kilometers above the surface. It took pictures of regions Mariner 10 had never seen. About half of the previously unmapped 60% of Mercury's surface was captured during this single flyby. The second Mercury flyby came on October 6, 2008, completing most of the rest of the surface coverage. The third Mercury flyby was on September 29, 2009. Throughout the cruise, between the flybys, the engineering team at the Johns Hopkins University Applied Physics Laboratory was managing the spacecraft from the ground. APL had built Messenger for NASA. The team was relatively small by the standards of large flagship missions, but they had been on the spacecraft from before launch and would be on it through orbital insertion and through the entire orbital mission. Some of them had been on it since the project began, in some cases for the better part of a decade before launch. The Mercury team was, in the way these teams always are, a small group of people who knew the spacecraft personally, knew which thrusters had been quirky during checkout, knew which radio configurations had performed best, knew the spacecraft's habits the way a sailor knows a particular boat. One unexpected thing the team learned during the cruise was that the spacecraft's solar panels could be used as braking sails. This was not a feature designed into the spacecraft from the start. It was a discovery made during the early years of the cruise, when the engineering team realized that the pressure of sunlight on the solar panels, while tiny, was not zero, and that over the course of a mission lasting years, even a tiny continuous deceleration could accumulate into a meaningful change in trajectory. By tilting the solar panels to specific angles relative to the Sun, the spacecraft could brake very gently against solar radiation pressure. The team began using this technique to save fuel. Over the course of the cruise, the technique saved enough fuel to extend the orbital mission far beyond its original plan. The reason this matters, the reason it is worth pausing on, is that even the cleverest pre-mission trajectory designed Chen Wan-yen's route, with its 3 Mercury flybys and its multi-year arc, was not enough by itself. The mission was extended by additional cleverness, discovered in flight, by a team that had to look at a familiar piece of hardware and see something nobody had seen before. This is what space exploration is actually like. It is not a single clever idea. It is one clever idea after another, found in different places at different times by people who keep looking. After the third Mercury flyby, Messenger continued in its slow heliocentric arc, looping the Sun and gradually closing the gap between its own velocity and Mercury's. On March 11th, 2011, Messenger was finally moving slowly enough relative to Mercury for the main engine to slot the probe into orbit. That night, at APL, The operations team gathered in the mission control room for the orbital insertion burn. The burn would last about 15 minutes. The geometry meant that the spacecraft would be behind Mercury, out of direct sight from Earth, for parts of the burn. The communication delay between Earth and Mercury at that moment was about 13 minutes one way. There was nothing the team on the ground could do during the burn. The spacecraft would either succeed or it would not. The instructions had been written, tested, uploaded, and verified weeks in advance. The team could only watch the telemetry that did make it back, pass the Doppler shift of the radio signal to confirm that the spacecraft's velocity was changing the way the burn plan said it should, and wait. The carrier signal stayed steady. The Doppler shift matched the plan. The burn ended. Messenger reported, after the geometry allowed it to, that the orbital insertion had succeeded. The probe was in orbit around Mercury. The first spacecraft to ever orbit the planet closest to the Sun, a 37-year gap in human exploration of the inner solar system, had just been closed. The orbit Messenger took was deliberately strange. It was not circular. It was deeply eccentric, swinging between about 200 kilometers above Mercury's surface at its closest point, and about 15,000 kilometers above the surface at its farthest. The reason for the eccentricity was thermal. Mercury's surface, in the bright sunlit half, is hot enough to reach about 806 degrees Fahrenheit, or about 430 degrees Celsius, hot enough to melt lead. That heat radiates outward. The surface acts, in a small way, like a giant solar mirror, reflecting and re-emitting energy back into space. A spacecraft sitting in low orbit around Mercury would not just face the Sun on one side, it would face Mercury's hot surface on the other side. Both sides would be cooking it. Even with the sunshade, lingering close to Mercury for too long would damage the electronics. The eccentric orbit gave Messenger a cooling period. During each swing, it would sweep low, gather close-range data quickly, and then swing back out into the cooler region of its orbit before coming around for another low pass. This is what I want you to feel, slowly, before we move on to the discoveries themselves. The Sun is 7 times brighter at Mercury than it is at Earth. The surface temperature is enough to liquefy most metals you can name. The probe, hanging in orbit around the planet, is in the harshest, sustained thermal environment any orbital spacecraft has ever been asked to survive. And the only way to survive it is to engineer an orbit that breathes that swings down and back up, like a long, slow lung, giving the spacecraft time to cool between glances at the planet beneath it, 7 years to arrive. 4.9 billion miles, 6 gravity assists, a sunshade, solar panels turned into braking sails, an orbit designed for thermal survival. All of it, the entire architecture, to spend 4 years mapping a planet only 48 million miles away at its closest. The phrase "to hold," while we move on to what the mission actually found, is the same phrase you have been hearing. Close is not easy. By the time Messenger was in orbit around Mercury, that phrase had a kind of physical weight that no other planet had yet given it, and it was earned. Part 6. What Messenger found and how it died. For 4 years, from March 2011 to April 2015, Messenger worked. The orbital phase of the mission was originally scheduled to last 1 Earth year. It was extended, and extended again. By the end, the spacecraft had been operating in orbit around Mercury for more than 4 times its original planned duration, returning data the entire time. The science return was enormous, and it remade our understanding of the planet closest to the Sun in ways that the elementary school version of the solar system has not yet caught up with. The first thing Messenger did was finish what Mariner 10 had started: map the surface, the full surface, not 40%, not 70%, but, eventually, the entire planet. Every crater, every basin, every ridge, every plain. The maps that exist today of Mercury's surface, the maps you can find in any current atlas of the solar system, are Messenger's maps. Before Messenger, 60% of Mercury was a blank space on every chart humans had ever drawn. After Messenger, the blank space was gone. The maps showed a world that was not what most planetary scientists had expected. Mercury looks, at first glance, a great deal like the Moon, a small, rocky, heavily cratered body, the kind of object that gets shaped by impacts and then settles down for the rest of geological time. But Messenger's images and altimetry revealed features that the Moon does not have. Long, sinuous cliffs called lobate scarps, running for hundreds of kilometers across the surface, marking places where the planet's crust had buckled and shifted as the planet's interior cooled and contracted. The amount of contraction implied was striking. Mercury seemed to have shrunk in radius by several kilometers over the course of its history. Whole regions of the surface bore the signature of volcanic activity that was relatively young by planetary standards. Smooth plains laid down by lava flows, hundreds of millions of years more recently than anyone had expected. The picture that emerged was not of a long-dead world, but of a world that had been geologically alive much later in solar system history than the textbooks had said. The magnetic field, the same one Mariner 10 had been surprised to detect, turned out to be even stranger than anticipated. It was offset from the planet's center by a significant fraction of Mercury's radius. The magnetic poles were not at the geographic poles, and the field as a whole was asymmetric, much stronger in the northern hemisphere than in the southern. Nobody fully understands why. The leading hypothesis involves an actively convecting liquid outer core in Mercury's interior, which is itself surprising a body that small was expected to have a frozen core by now. Mercury's interior is, evidently, still doing things. The chemistry of the surface, mapped by Messenger's spectrometers, was also not what anyone expected. Mercury was thought to be a sun-baked, volatile, poor world, stripped of light elements by the heat of its environment. Messenger found surprising abundances of volatile elements: sulfur, sodium, potassium, chlorine. The composition was not the desiccated rocky body the prior model had described. Mercury had retained, somehow, a chemistry richer in volatiles than anyone had predicted for a planet so close to the Sun. And then, the most striking discovery of all: Mercury has water ice. You have to sit with this for a moment, because the words "Mercury has water ice" sit so far outside the intuition of a planet baked to over 800 degrees Fahrenheit that they sound like an error. Mercury, of all the planets, was supposed to be the place where water could not survive. Mercury sits closer to the Sun than any other planet. The day side reaches temperatures that would vaporize water instantly. The very atmosphere, what little atmosphere Mercury has, is so thin that any water molecule released to the surface should boil off into space within hours. But Mercury has a small axial tilt. Its rotation axis is almost perfectly perpendicular to its orbital plane. That tiny tilt means that, near the poles, there are crater floors that the Sun, in the geometry of Mercury's rotation, never reaches. Deep craters, with high rims, casting permanent shadows over their interiors. Inside those permanent shadows, the temperature never rises. The crater floors stay frigid, well below the freezing point of water, for billions of years. And in those permanent shadows, water ice can survive. Messenger's neutron spectrometer mapped the hydrogen content of Mercury's polar regions and found exactly where the geometry predicted it should be: enhanced hydrogen signatures in the permanently shadowed crater floors at both poles. The pattern was unmistakable. The simplest explanation, and the one the data supported, was that there was water ice in those craters. Possibly billions of tons of it, sitting in permanent shadow on the hottest planet in the inner solar system. The Earth-based radar observations of the 1990s had hinted at this. The MESSENGER measurements confirmed it. The planet closest to the Sun is one of the only places in the inner solar system with confirmed surface water in any form. There is something to feel about this discovery. Slowly, the way you feel a paradox settle into a coherent fact in the back of your mind. The universe is, in a quiet way, more accommodating than its harshest places suggest. Even on Mercury, the planet you would expect to be the most thoroughly inhospitable rocky body in the inner solar system, the universe leaves a small, protected place where something fragile, something you would expect to be impossible, can persist for billions of years. Ice survives on the planet next to the furnace. The protected place is the bottom of a shadow. The protection is not technology, not engineering, not intention. The protection is geometry, a small tilt of an axis, a deep crater, a high rim, a corner of the planet that never sees the sun. This is one of the deep emotional anchors of the entire story. The hardest place to reach yielded the most counterintuitive answer. The closest planet to the sun is also the closest planet to the sun that has ice. The thing that should be impossible turns out to be ordinary, in its way, once you let the geometry teach you what survival actually looks like. For 4 years, MESSENGER kept mapping, kept measuring, kept refining, kept revising the model of what a small inner planet is. And then the fuel ran out. On April 30th, 2015, the last drops of propellant in MESSENGER's tanks were exhausted. The spacecraft had been making small maneuvers throughout the mission to keep its orbit from decaying. Mercury's gravitational geometry is such that, without active station keeping, an orbiting spacecraft will eventually be pulled down to impact. The fuel had been running out for months. The team had known the date was coming. They had planned for it. The end of MESSENGER was, like the end of Galileo at Jupiter and the end of Cassini at Saturn, a deliberate impact. The spacecraft, no longer able to maneuver, was allowed to follow its natural trajectory down to the surface of Mercury. On April 30th, at approximately 3:26 in the afternoon Eastern Daylight Time, MESSENGER struck Mercury's surface on the planet's far side at a speed of about 8,750 miles per hour. The impact created a small crater, somewhere on the part of Mercury we now know down to the meter level, because MESSENGER had finished mapping it. That was the end of MESSENGER. The 30-year silence had been broken, and now there was, again, no spacecraft at Mercury, but the next one was already on its way. Bepi Colombo launched on October 20th, 2018, from the ESA spaceport at Kourou. Bepi Colombo is a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, named for the Italian astronomer Giuseppe Bepi Colombo, who in the 1960s had been the first person to recognize the gravity assist trajectory that Mariner 10 would later use. The mission carries 2 orbiters bundled together with a transfer module, a Mercury planetary orbiter, built primarily by ESA, and a Mercury magnetospheric orbiter, called MEO, built primarily by JAXA. Like MESSENGER, Bepi Colombo flies a multi-flyby trajectory in the family of routes Chen Wan-yen had pioneered. Multiple Earth, Venus, and Mercury flybys. A long cruise, a patient arrival. Bepi Colombo is still cruising. The most recent Mercury flyby was earlier this year. The Mercury orbital insertion is currently planned for late 2026, after which the 2 orbiters will separate and begin their own science campaigns at the planet. The mission will, if all goes as planned, hand the next generation of Mercury science off to a new orbital pair, building on what MESSENGER established. That is the Mercury story. 30 years of silence, broken by one trajectory designer in 1985, made real by a 7-year mission in 2004, ending in deliberate impact in 2015, and continued by a follow-up, the that has been cruising for 8 years and is still en route as we record this. The phrase, once more, close is not easy. Mercury, the planet next door, taught us that more fully than any other planet in the inner solar system ever could. And every story about every other planet that follows from here is, in one form or another, a different verse of the same lesson. Mars's hardness is fuel, Jupiter's hardness is radiation, Saturn's hardness is time. The ice giant's hardness is sunlight. Pluto's hardness is distance and patience. Mercury's hardness was the sun's gravity well, the deepest version of closed but impossible that the inner solar system has to offer. We have now climbed out of that well. We are going to spend the rest of the story climbing outward, planet by planet, watching the obstacles change, watching the lessons stay the same. Part 7. Mars and the Distance Problem. After Mercury, the next planet in our outward walk is Venus. And Venus deserves more time than we have for it tonight, because Venus is its own kind of difficult. The surface is hot enough to melt lead. The atmospheric pressure is about 90 times Earth's at the surface. Every lander the Soviet Union sent in the 1970s and 80s survived only minutes before being crushed. But Venus is not where our story turns next. Our story turns next to Mars, because Mars is the planet where the difficulty stops being about exotic physics like the sun's gravity well, and starts being about a different kind of hard. The kind of hard that has to do, simply, with how far away a thing is, and how much fuel it takes to go there, and how much time a human body and mind can withstand. Mars is the first planet on this list where distance, by itself, is the dominant constraint. And distance, on the scale of a Mars mission, turns out to mean something much larger than the number of miles between 2 points. The minimum distance between Earth and Mars during one of the periodic close approaches that happens about every 26 months is about 55 million kilometers. The maximum distance is much larger, up to about 400 million kilometers, when the two planets are on opposite sides of the Sun. The average is somewhere in between, around 225 million kilometers, depending on how you compute it. Compared to the distance from Earth to the International Space Station, which sits about 400 kilometers above the surface, about the same distance as the straight line from Madrid to Almeria, Mars, is roughly 1 million times farther away. A single one-way trip to Mars is, in straight-line distance, equivalent to about 1 million round trips to the ISS. To feel what that means, start with a smaller scale and walk outward. The International Space Station, which has been continuously occupied since the year 2000, orbits at about 400 kilometers up closer to your house than most major cities. The Moon is about 380,000 kilometers away, 1,000 times farther than the ISS. The Apollo program, between 1969 and 1972, sent 12 people to the lunar surface across 6 missions on 9 Saturn V launches. The Saturn V was, and still is, the most powerful operational rocket ever flown, about 3,000 tons at launch, 110 meters tall, capable of putting 120 tons into low Earth orbit and sending 50 tons on a trajectory toward the Moon. Mars is 1,000 times farther away than the Moon, and that 1,000-fold leap changes everything about the architecture of a mission. Here is what a Mars mission profile actually looks like when you do the math. A typical baseline study, the kind NASA and various international partners have done many times, assumes a crew of 6 astronauts. The mission would launch during an Earth-Mars approach gap to take advantage of favorable orbital geometry. The outbound transit, the cruise from Earth to Mars, would last about 174 days, just under 6 months. Then the crew would be on Mars for about 539 days, almost a year and a half, waiting for the next favorable geometry to make the return trip with reasonable fuel cost. Then the return transit, about 201 days, another 6.5 months. Total mission duration, about 914 days, about 2.5 years. That is the baseline. 2.5 years, away from Earth, 6 astronauts, on a journey 1,000 times more remote than anything humans have ever attempted with crew before. The fuel required for this mission is the kind of number that, the first time you hear it, sounds impossible. Estimates vary depending on architecture, but for a round-trip crewed mission, with all the cargo and life support and propellant for return, you are looking at somewhere between 850 and 1,250 tons of fuel. Not the spacecraft, just the fuel. For comparison, the entire International Space Station, after decades of assembly, has a total mass of about 420 tons. A Mars mission's fuel alone is 2 to 3 times the mass of the entire ISS. The Space Shuttle, when it was operating, could lift about 15 to 25 tons to low Earth orbit per launch. The Ariane 5 rocket can lift about 20 tons. The Russian Proton, similar. Even the modern Falcon Heavy and Starship and the Space Launch System are in the same general performance class as the old Saturn V, capable of putting roughly 120 tons into low Earth orbit, or sending roughly 50 tons toward the Moon. To assemble the fuel and hardware for a single crewed Mars mission by any of these rockets, you are looking at on the order of 10 launches of a Saturn V-class rocket. The entire Apollo program flew 9 Saturn Vs. A single Mars mission, by this accounting, would require more heavy-lift launches than the entire program that put humans on the Moon. This is the second big realization of the Mars problem, the fuel mass curse. Every kilogram of payload you want to land on Mars and bring home requires a much larger amount of fuel. That fuel has its own mass, which requires more fuel to accelerate, which has its own mass, which requires more fuel to accelerate. This is the consequence of Tsiolkovsky's rocket equation, written in 1897. For large velocity changes like the ones needed to leave Earth, brake at Mars, leave Mars, and brake back at Earth, the equation turns exponential against you. Most of your mass has to be fuel. Most of that fuel exists only to push the rest of the fuel. The amount of useful payload at the end is a tiny sliver of the total mass at the beginning. There are, in principle, ways out of this. One is in situ resource utilization, landing on Mars and manufacturing the return fuel from the materials available there, using water in the regolith and carbon dioxide in the atmosphere to produce methane and oxygen. NASA has been studying this for decades, and the Mars 2020 rover demonstrated, on the surface, the production of oxygen from atmospheric carbon dioxide. The principle works at small scales. The engineering of doing this at mission scale, reliably, where any failure means the crew has no return vehicle, is still ahead of us. So, the fuel mass is one part of the Mars hardness. The other part is the time, 914 days, 2.5 years. 6 people in a small pressurized volume on a journey of which there is no shortening. 2.5 years in space is not a duration the human body has been tested against in deep space ever. The longest single human spaceflight is currently around 438 days by Valery Polyakov on Mir in the 1990s. That was in low Earth orbit, inside the Earth's magnetic field, with regular cargo resupply and continuous real-time communications with home. A Mars mission has none of those advantages. Outside the magnetosphere, the crew is exposed to cosmic radiation that Earth's field would otherwise deflect. The radiation dose accumulates the entire trip. The shielding to reduce that risk is mass. Mass is fuel. Fuel is more mass. Then there is microgravity. The human body, on Earth, is constantly resisting gravity. Bones load, muscles work. Take that gravity vector away, and the body begins to remodel. Bones lose density. Muscle mass decreases. The cardiovascular system weakens. The eyes, oddly, change shape. All of these can be mitigated, partially, by aggressive exercise programs. None can be fully prevented. After 900 days in space, a crew arriving at Mars will arrive in bodies that are, in real and measurable ways, less robust than the bodies that left. Then the psychology. 2.5 years of confinement, with the same 5 other people, in a space the size of a small house. Earth shrinks from a recognizable disk in the window during the first weeks to a small point of light by month 2. Real-time conversation, even at the speed of light, is impossible. The Earth-Mars communication latency is between 3 and 22 minutes one way. A conversation with a loved one back home is not a conversation. It is a series of recorded messages with multi-minute delays between them. The crew, for most of the mission, is fundamentally alone. And then there is the question of what breaks. The longer the mission, the more things have a chance to fail. The ISS, after 25 years of continuous operation, has a list of components that need regular replacement fans, pumps, water reclamation hardware, life support filters, batteries. Cargo flights from Earth bring replacement parts every few months. A Mars mission gets no resupply. Anything that breaks during the cruise has to be repaired with what is on board or done without. The spacecraft has to be designed not just to last 900 days, but to be repairable by the crew for any failure that is conceivable, with the tools and spare parts they can afford to carry. That redundancy adds mass. Mass is fuel, so that is Mars. The hardness is distance. But the hardness is also fuel, and time, and radiation, and psychology, and repair logistics, and the realization that all of these problems compound. Reaching Mars is not one hard problem. It is a dozen hard problems, woven together, each one making the others worse. We are not, despite the popular framing, ready to send humans to Mars. The technology exists in pieces. The technology does not yet exist as a single, integrated, reliable, affordable system. The current best estimates from NASA, when they are honest about it, are that the first humans on Mars are decades away, not years away. The optimistic estimates put it within the lifetimes of people listening to this. The pessimistic estimates put it well beyond. What is striking, when you sit inside the Mars problem long enough, is how different a kind of hard it is from Mercury's hard. Mercury was solved by one person finding a clever route through the sun's gravity well. The math allowed it. Mars is not waiting for one person to find a clever route. The math of getting to Mars is well understood. The problem is that the math demands an architecture that we do not, as a species, currently know how to afford and operate. Mars is hard, not because the universe hides the solution. Mars is hard because the universe gives us the solution honestly, and the bill is enormous. The phrase to remember, close is not easy. And distance for Mars, finally, actually is hard. Distance is the dominant variable here, and you can feel the variable doing its work in every aspect of the mission, from the fuel curve to the radiation dose to the loneliness of the crew. The variable is not always the same one. We will find this again at Jupiter, and again at Saturn, and again at the ice giants. Each planet picks a different variable. Each planet is hard in its own particular way. The outer planets are next. We have left the inner solar system. We are now going to find out what hard means when distance is not the only difficulty, and the universe begins to bring out variables that the inner solar system never showed us. Part 8. Jupiter and Saturn, Radiation and Rings. When you cross the asteroid belt outbound from Mars, something changes about the solar system. The inner system you have been crossing, Mercury, Venus, Earth, Mars, was a place of small, rocky worlds, each one a few thousand kilometers across, each one with a surface a spacecraft could in principle stand on. The outer solar system is a different country. The first thing you reach is Jupiter. And Jupiter is, in a way that takes some time to absorb, not a planet at all, in the sense the inner planets are planets. Jupiter is a giant ball of fluid, mostly hydrogen and helium, with no defined surface anywhere, just a smooth gradient, from gas to liquid to deep in the interior, an exotic state where hydrogen is compressed so hard it behaves like a liquid metal. You cannot land on Jupiter. There is nothing to land on. The atmosphere just gets thicker, hotter, and more pressurized the deeper you go, until it crushes anything you send into it. So Jupiter, on the face of it, is hard to reach in a completely different sense than Mercury. There is no surface to map. There is no landing site. There is just an enormous atmosphere, 11 times the diameter of Earth and 318 times Earth's mass, hanging in the outer solar system like a small failed star. But here is the first surprise about Jupiter, the one that bends intuition the same way the Sun's gravity well bent intuition for Mercury. Jupiter is, in terms of raw energy to fly to, not that much harder than reaching low Earth orbit. The amount of energy required to lift a spacecraft from Earth's surface to a Jupiter flyby trajectory is, in rough numbers, about the same as the amount required to put that spacecraft into low Earth orbit. Both energies are dominated by the cost of climbing out of Earth's own gravity well. Once you have done that, sending the spacecraft outward to Jupiter is almost free by comparison. The Sun's pull, at Jupiter's distance, is so much weaker than it is at Earth's distance that the spacecraft, once launched, just coasts. The journey is long. Voyager 1 took 1,546 days, just over 4¼ years, to reach Jupiter from launch, but it is not energetically demanding. The first probes to visit Jupiter Pioneer 10 and Pioneer 11, then Voyager 1 and Voyager 2 were all flybys. They came, took pictures, used Jupiter's gravity to slingshot further outward, and left. From them, we learned that Jupiter is mostly liquid in the bulk of its interior. We learned that its magnetic field is so enormous that the entire solar system's planets could fit inside its volume. We learned that the Great Red Spot is an anticyclone that has been blowing for at least 3½ centuries. We learned that Jupiter has its own faint ring system. And we learned that the 4 large Galilean moons were not boring icy companions, but worlds with their own geology, chemistry, atmospheres, and in some cases, subsurface oceans. But to actually orbit Jupiter, rather than just fly past, is a much harder problem. The reason has nothing to do with distance. The reasons are 2: gravity capture and radiation. Gravity capture first. A flyby is easy because the spacecraft does not need to stop. For an orbiter, the spacecraft has to slow down enough during the encounter that Jupiter's gravity captures it. Jupiter's gravity is the largest in the solar system after the Sun's. Capture requires a significant velocity change. That velocity change requires fuel. The fuel mass curse shows up again. Voyager 1 and Voyager 2 were both moving too fast. On arrival, to be captured, they were Grand Tour spacecraft, designed to fly past everything. Galileo, the first dedicated Jupiter orbiter, was different. It carried a main engine specifically designed to break into Jupiter orbit on arrival. Galileo launched in 1989 from the Space Shuttle. It took 6 years to reach Jupiter, with multiple gravity assist flybys of Venus and Earth on the way to gain enough velocity for the outbound transit. It arrived at Jupiter in December 1995. On the way in, it released a small atmospheric probe, a separate piece of hardware designed to plunge directly into Jupiter's atmosphere and transmit data on the way down. The atmospheric probe entered Jupiter on December 7, 1995. It survived for 57.6 minutes, descending about 150 kilometers through the upper layers of the atmosphere, returning data on composition and temperature and pressure and wind. At about 22 times Earth's atmospheric pressure and temperatures approaching 150 degrees Celsius, the probe was destroyed. It was vaporized somewhere deeper in the atmosphere, dust by now, lost in Jupiter's interior. Meanwhile, the main Galileo orbiter fired its braking engine and slid into Jupiter orbit. For the next 8 years, Galileo studied Jupiter and its moons. The mission had been crippled, partially, by a failure on the way out. The spacecraft's main high-gain antenna had failed to deploy correctly during the cruise and could never be fully opened. The mission was rescued by using a low-gain antenna and developing aggressive data compression techniques on the ground to make the most of the limited bandwidth. It was a workaround. It was the kind of workaround that defines space exploration when the universe refuses to cooperate. The mission survived. The science was returned. The second hard part of orbiting Jupiter, the one that eventually kills any spacecraft that stays long enough, is radiation. Jupiter has the most intense radiation belts of any planet in the solar system. Charged particles, trapped by the magnetic field, accelerate to relativistic velocities and bathe everything inside the belts in continuous high-energy radiation. Galileo, by the end of its mission, had absorbed many times the design tolerance of its electronics. The spacecraft suffered increasing glitches as components degraded. The mission was ended deliberately on September 21, 2003, by sending the spacecraft into Jupiter's atmosphere, not because it had to be destroyed, but to prevent any possibility of Galileo crashing into Europa and contaminating that moon's subsurface ocean. This patterned, deliberate impact at end of mission to protect potentially habitable moons became, after Galileo, the standard ending for outer planets' orbiters. Cassini, at Saturn, would end the same way. Juno, the current Jupiter orbiter, is planned to end the same way. The phrase, end of mission, no longer means we lose contact. It means we drive the spacecraft into the planet, on purpose, to make absolutely certain nothing of ours ever lands somewhere life might exist. Juno is the current Jupiter mission. It launched in 2011. It entered orbit around Jupiter on July 4, 2016. It is on a deliberately strange polar orbit, coming in over Jupiter's north pole, swinging close to the cloud tops, and going back out over the south pole, threading between Jupiter's most intense radiation belts on each pass. The polar orbit is designed to minimize the radiation dose, because the worst of the belts is concentrated in Jupiter's equatorial plane. Juno still takes damage with each pass, but at a rate slow enough to allow a multi-year mission. It has been operating in Jupiter orbit for almost a decade now, mapping Jupiter's gravity field, magnetic field, deep atmospheric structure, polar auroras, and producing some of the most spectacular images of the planet ever made. Juno is scheduled to end its mission with a deliberate impact when the radiation finally takes too much from it, on the same model as Galileo. And the European Space Agency has, this decade, launched a new outer planets mission. JUICE, the Jupiter Icy Moons Explorer, launched in April 2023. JUICE is not aimed at Jupiter itself, but at its 3 large icy moons, Ganymede, Callisto, and Europa. The mission will arrive at Jupiter in 2031 and spend years studying the moons up close, including a final orbital phase around Ganymede, the first time any spacecraft will orbit a moon of another planet. JUICE is the recognition that the most interesting things at Jupiter are not the planet itself, but the moons that orbit it, and that those moons, with their subsurface oceans, may be the most plausible sites for life elsewhere in the solar system. Saturn is, in many respects, Jupiter's cousin, also a gas giant, also no surface, also a complex moon system, and, of course, the planet with the rings, the most visually distinctive object in the solar system. Galileo first saw the rings through a telescope in 1610, but could not resolve them. Christian Huygens, in 1659, correctly identified them as a disconnected ring system. James Clerk Maxwell, in 1859, proved mathematically that the rings could not be solid. They had to be made of countless small particles, each in its own independent orbit. We now know those particles are predominantly water ice, orbiting at about 48,000 kilometers per hour, 15 times the speed of a typical rifle bullet. To reach Saturn is, in energy terms, only modestly more demanding than reaching Jupiter. The probes that have visited Saturn have all used Jupiter as a gravity assist accelerator on the way out. Pioneer 11 reached Saturn in 1979, Voyager 1 in 1980, Voyager 2 in 1981. All three were flybys. Then Cassini-Huygens, a flagship-class mission with NASA, ESA, and the Italian Space Agency, as partners launched in 1997, reached Saturn in 2004 and orbited the planet for 13 years. Cassini is one of the great missions of the modern planetary era. The orbiter mapped Saturn's atmosphere in detail, watched storms develop and decay, characterized the rings to a resolution unimaginable to Maxwell, and visited every major moon at close range. The companion spacecraft, Huygens, built by ESA, separated from Cassini after arrival and parachuted to the surface of Titan on January 14, 2005. The Huygens landing remains the only landing on a body in the outer solar system. Huygens transmitted from Titan's surface for about 90 minutes. The images showed gentle hills, dry channels apparently carved by liquid flow, and a surface covered in pebbles of water ice. Titan has weather, but Titan's weather is methane. At minus 179 degrees Celsius, methane plays the role water plays on Earth. Methane clouds, methane rain, methane rivers, methane lakes in the polar regions. Cassini ended in 2017 with another deliberate impact. The grand finale, a series of 20 orbits that took the spacecraft through the narrow gap between Saturn and the innermost edge of its rings, returning unprecedented close-range data on Saturn's atmosphere, concluded with Cassini diving into Saturn's atmosphere on September 15, 2017. The same logic as Galileo. Cassini could not be allowed to drift uncontrolled and possibly contaminate Enceladus, the small icy moon whose subsurface ocean Cassini had itself discovered and whose geysers Cassini had flown through, sampling the water vapor for chemistry. The next mission to Saturn is being designed now. It is called Dragonfly, and it is not an orbiter. It is a rotorcraft, a drone, in essence, that will fly through Titan's thick atmosphere, landing in different places to study Titan's surface chemistry and prebiotic conditions. Dragonfly is scheduled for launch in 2028 and arrival at Titan in 2034. 26 years after the first Cassini close-range data, we are going to send a flying laboratory to the methane world. The phrase, once more, in a different key, close is not easy. Jupiter is far, but not energetically far. The hardness was radiation, gravity capture, and the long mission timeline. Saturn was the same hardness, magnified by additional distance, plus the institutional challenge of holding a flagship mission team together for the 7 years of cruise and the 13 years of operations, a 20-year span across which engineering careers begin and end. The variable is not the same for every planet. The lesson is the same lesson. Outside Saturn, the variables change again. The sunlight gets too faint for solar panels. The signal delays start to break the assumption of real-time control. The flight times start to span generations. The ice giants are next, and Uranus and Neptune are the planets where, in some real sense, we have not even started. Part 9. The Ice Giants and the Sunlight Problem. Past Saturn, the solar system thins out. No more obvious icons of the night sky. Uranus and Neptune are visible from Earth, but only barely. Uranus is at the edge of naked eye visibility. Under perfect dark sky conditions, Neptune requires a telescope. Both were discovered in the eras of mathematical astronomy. Uranus was discovered by William Herschel in 1781 by accident while systematically scanning the sky. Neptune was discovered in 1846 by Johann Gaia, working from a position predicted by Urbain Le Verrier from tiny gravitational perturbations in Uranus's orbit. Neptune was, in a real sense, found by mathematics before it was found by a telescope. These are the ice giants. They are not, despite their name, made primarily of ice in the everyday sense. They are made of substances that, at the temperatures and pressures of their interiors, behave like a fluid planetary scientists call ice water, ammonia, and methane in compressed exotic states. Uranus has about 60 times the volume of Earth, Neptune about 57 times. Both have thick hydrogen-helium atmospheres on top of their ice mantles and rocky icy cores beneath. Uranus has the coldest planetary atmosphere in the solar system, with a minimum temperature of about 49 Kelvin, about negative 224 degrees Celsius. Neptune, oddly, is warmer than Uranus despite being farther from the Sun. Neptune radiates more energy than it receives from the Sun. Uranus appears not to. The mechanism is not fully understood. Uranus is one of the strangest worlds in the solar system, in a way that has nothing to do with composition. The axis of rotation is tilted by 97.77 degrees. The planet rotates on its side. The leading hypothesis is that during formation, Uranus suffered a glancing collision with an Earth-sized protoplanet, an impact violent enough to knock the planet over, but not violent enough to disrupt it. The atmosphere relaxed any features the impact created. The only evidence is the tilt itself. The consequence is that Uranus has the strangest seasons of any planet. Each pole spends about 42 years in continuous sunlight, followed by 42 years in continuous darkness. Imagine the sun, instead of rising and setting once a day, rising slowly over the course of a decade, hanging in the sky for 42 Earth years, and then setting again over the course of another decade. The most recent equinox of Uranus, when the day-night cycle briefly became Earth-like, was on December 7th, 2007. The next will be in 2049. Neptune is more conventional in its tilt about 29 degrees, similar to Earth's 23.5. But Neptune has its own strangeness. Its winds are the fastest in the solar system. Voyager 2, during its single flyby in 1989, measured winds in Neptune's atmosphere reaching about 600 meters per second, or about 2,200 kilometers per hour. That is almost the speed of sound in Earth's atmosphere supersonic relative to the local conditions on Neptune. The wind speeds make no obvious sense thermodynamically. At Neptune's distance from the Sun, the sunlight that reaches the planet is less than 0.1% of what reaches Earth. The atmospheric temperature near the cloud tops is about negative 210 degrees Celsius. There is almost no solar energy available to drive winds at those speeds. The energy has to come from inside the planet, from heat left over from formation, slowly bleeding outward from the interior. Neptune is, in a sense, still warm from being born more than 4 billion years ago. And then there is Triton. Triton is Neptune's largest moon, almost as large as Earth's moon, 2,707 kilometers in diameter. It is one of the most interesting objects in the solar system, and it does not belong to Neptune in the same way the other large moons belong to their planets. Triton orbits Neptune backwards retrograde, in the opposite direction to Neptune's rotation. No other large moon in the solar system does this. The retrograde orbit, combined with Triton's composition, which closely matches the composition of Pluto and other Kuiper Belt objects, almost certainly means Triton is not a moon at all. in the original sense. Triton is a Kuiper belt body that wandered too close to Neptune billions of years ago and was captured. Neptune, in some real sense, stole Triton from the outer solar system. Voyager 2 photographed Triton during its flyby in 1989. The images showed a world with a remarkably young surface, few craters, suggesting active geological resurfacing. They also showed something nobody had expected on such a small, cold body: active cryovolcanism. Plumes of nitrogen gas, mixed with dust and methane, were rising from the surface to heights of about 8 kilometers and being carried downwind by the planet's thin atmosphere. Triton is volcanically active, not with rock, but with nitrogen. It is one of only 7 bodies in the solar system known to have active volcanic activity: Earth, Io, Venus, Europa, Enceladus, Titan, and Triton. The other 6 are either large or warm. Triton is neither. Whatever drives its activity has to come from a combination of solar heating of nitrogen ice in the upper layers and possibly tidal heating from Neptune. We do not fully understand it. We have not been back to look since 1989. That is the deepest single fact about the ice giants. We have not been back. Voyager 2 is, to date, the only spacecraft that has ever flown by Uranus or Neptune. The Uranus flyby was on January 24th, 1986, 40 years ago. The Neptune flyby was on August 25th, 1989, 37 years ago. No orbiter has ever flown to either planet. No follow-up mission has been launched. The data we have on the ice giants is the data Voyager 2 collected during a few hours of close approach to each almost 4 decades ago. Why? Why have these worlds been so thoroughly ignored? The answer is, again, not distance alone. It is the combination of variables that distance brings with it. The first variable is sunlight. At Uranus's distance from the Sun, the intensity of sunlight is about 1/400th of what it is at Earth. At Neptune's distance, it is about 1/900th. Solar panels do not work, in any practical sense, at those distances. The light is too feeble. A spacecraft sent to Uranus or Neptune cannot run on solar power. It has to run on a radioisotope thermoelectric generator, a nuclear battery. The standard fuel is plutonium-238, an isotope that decays slowly and releases heat for decades, which is converted to electricity by thermocouples. RTGs have powered every outer planet's mission since Pioneer, 10 Pioneer, Voyager, Galileo, Cassini, New Horizons, all of them. But plutonium-238 is hard to make. The United States stopped producing it for a long stretch, starting in the late 1980s, and only restarted production at Oak Ridge National Laboratory in 2013. Current production is on the order of 1.5 kilograms per year. A single large RTG requires several kilograms. The supply chain is a real constraint on how many outer planets missions we can fly. The second variable is communication latency. A spacecraft at Uranus is between 15 and 23 minutes from Earth at the speed of light, depending on the orbital geometry. Round trip is between 30 and 46 minutes. At Neptune, the numbers are larger. Real-time control is impossible. Any spacecraft at the ice giants has to make its own decisions in the moment about most of what it does, with general guidance from Earth on broader plans. The autonomy required is substantial. The third variable is flight time. A direct trajectory from Earth to Uranus, with a Jupiter gravity assist, takes about 10 to 15 years. To Neptune, with the same kind of assist, about 12 to 15 years. Add the cruise time to the operational time, and you are designing a mission that, from initial concept to end of operations, will span 2 to 3 decades. The engineering team that starts the mission is not the engineering team that finishes it. The flight controllers who eventually managed the spacecraft at the planet were sometimes children when the mission was approved. this is not a marginal problem. It is one of the deep, practical reasons that ice giant missions keep being studied and not flown. The institutional commitment required is much more demanding than the institutional commitment required for shorter missions. Personnel turnover, funding cycles change, political support shifts. A Uranus or Neptune mission has to survive multiple presidential administrations, multiple agency leadership changes, multiple budget cycles, before it ever begins returning data. Over the past 2 decades, NASA has repeatedly studied the question of a flagship-class mission to one of the ice giants. The 2023 Planetary Science Decadal Survey, an independent assessment by the National Academies of Sciences, Engineering, and Medicine, identified a Uranus orbiter and atmospheric probe as the highest priority flagship mission for the coming decade. The recommendation is, by the standards of the Decadal Survey, unambiguous: Uranus first, yet the mission has not been funded. The Outer Planets Assessment Group, OPAG, has separately argued for Neptune over Uranus on the grounds that Triton's subsurface ocean potential makes Neptune the more scientifically valuable target. The debate continues. No mission has been confirmed. The technology to fly an ice giant orbiter exists. The willingness to commit institutionally to a 15-year wait repeatedly across multiple budget cycles does not reliably exist. So Uranus stands in the night sky, tilted on its side, in the middle of one of its 42-year polar seasons, with no spacecraft anywhere near it. Neptune stands in the night sky, with winds we do not understand and a captured moon we have not visited in nearly 40 years. The ice giants are the planets the solar system has kept for itself. We have looked at them from millions of kilometers away, for a few hours each, in 1986 and 1989, and that is all the close-range data we have. Everything else we know about them comes from the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories, looking from a distance of several billion kilometers. The phrase, once more, close, is not easy. And for the ice giants, the variable is not distance alone, but the constellation of variables that distance brings: sunlight, latency, mission duration, institutional memory. Every one of them is solvable. None of them, in combination, has yet been solved. The next chapter of the solar system, the part that includes a real understanding of Uranus and Neptune, is waiting for a generation that decides to commit to the long wait. So far, that generation has not been us. But there is one more planet, and one more difficulty, and one more chapter in this story before we reach the closing. Beyond Neptune lies the Kuiper Belt. And inside the Kuiper Belt sits Pluto, the body that for most of the 20th century was called the 9th planet, and the body whose mission to reach it took longer to authorize than the mission itself took to fly. We are going to spend the next part with the small probe that, in the end, reached the farthest planet anyone had ever visited. Part 10. Pluto and the Patience of the Small Probe. The story of how a spacecraft ever reached Pluto is, in its way, the most human chapter of this entire video. The other planets we have walked through were reached by missions that, while difficult, eventually got approved and flew. Pluto was different. Pluto was the planet that NASA and JPL and the planetary science community kept trying to send a mission to, and kept failing to send a mission to, for almost 30 years. The story of New Horizons, the probe that finally reached Pluto in 2015, is not really a story about a spacecraft. It is a story about the slow accumulation of patient effort by people who refused to let a planet go unvisited. It begins in 1964 at JPL with a young engineer named Gary Flandro. Flandro was working on the problem of trajectories to the outer planets. He noticed something. Over the course of 2 centuries or so, the giant planets of the solar system, Jupiter, Saturn, Uranus, Neptune, lined up in their orbits in a particular pattern, about once every 175 years. The next alignment was coming up, in the late 1970s. With the right trajectory, a single spacecraft could be launched in the late 70s, use Jupiter's gravity to slingshot to Saturn, use Saturn's gravity to slingshot to Uranus, use Uranus's gravity to slingshot to Neptune, and from Neptune, potentially, fling itself further outward. With another version of the trajectory, a different spacecraft could route through Jupiter, then Saturn, and out to Pluto. 2 spacecraft, 1 alignment, almost all of the outer solar system in a single multi-decade tour. The window would not come again until the late 22nd century. NASA, when Flandreau showed the work, was enthusiastic. The mission concept was called Grand Tour. 2 spacecraft, called TOPS thermoelectric outer planet spacecraft, would be built and launched in the mid-70s to use the alignment. Pluto was on the manifest. The encounter was scheduled for 1985 or 1986. Then NASA looked at the cost. Grand Tour was cancelled. Too expensive. The mission was reformulated, slimmed down, made cheaper, and relaunched as a more modest program. The 2 TOPS probes became 2 Voyager probes, smaller, lighter, less ambitious in scope, designed to fly the same trajectories, but with reduced instrument suites and reduced expectations. Voyager 1 was assigned the Jupiter-Saturn route. Voyager 2 was assigned the Jupiter-Saturn-Uranus-Neptune route. Voyager 1 had the option, after Saturn, of being directed either toward Pluto or toward a close flyby of Titan, Saturn's largest moon, and at the time, the only moon known to have a thick atmosphere. NASA chose Titan. Voyager 1 ended its planetary tour at Saturn and continued out of the solar system on a trajectory that took it nowhere near Pluto. Pluto, once again, was set aside. The reasoning was scientifically defensible. Titan was a known unknown, a moon with an atmosphere, possibly with weather, possibly with chemistry, possibly with prebiotic conditions. Pluto was a less known, unknown, small, distant, almost certainly cold and dead, with a tiny moon called Charon that had only been discovered in 1978. NASA chose Titan, and Voyager 1's pictures of Titan turned out to show a featureless orange smog, with the actual surface entirely hidden beneath the thick atmosphere. The Titan flyby was scientifically valuable but, in a sense, anticlimactic. And Pluto, the planet that had been on the original Grand Tour manifest, was now without a mission. The 1980s came and went. Plans for a Pluto mission were drafted and abandoned year after year. Pluto 350, proposed in 1989, was shelved as too lean. Pluto Fast Flyby, in the early 1990s, was shelved as too risky. Pluto Kuiper Express was shelved as not affordable. All through this period, planetary scientists watched a closing window. Pluto's atmosphere, composed of nitrogen and methane and carbon monoxide, is active during perihelion and freezes out during aphelion. The last perihelion was 1989. A mission needed to launch soon, or the atmosphere would be gone by arrival. The community kept pushing. Alan Stern, who had been working on Pluto mission concepts since the late 1980s, was one of the most persistent voices. NASA created a new program called New Frontiers for medium-cost outer planets missions too expensive for Discovery, too cheap for flagships in the Cassini class. In 2001, after a public competition, NASA selected New Horizons, a Pluto-bound spacecraft proposed by a team led by Stern at the Southwest Research Institute. The launch window was January 2006, with a backup in February 2007. After that, the next favorable Jupiter gravity assist would not come for years. New Horizons launched on time on January 19, 2006, on an Atlas V from Cape Canaveral. The spacecraft was the fastest object ever launched from Earth at the time, leaving Earth's gravity at about 16 kilometers per second. It crossed the Moon's orbit in about 9 hours, a journey that had taken Apollo about 3 days. Total spacecraft mass, including fuel, was 478 kilograms. Total mission cost was about $646 million in 2014 dollars, modest by flagship standards. The Jupiter gravity assist took place between February and March 2007. New Horizons swung past Jupiter and gained about 4,023 meters per second of velocity, shaving about 3 years off the cruise. Then, for 8 years, New Horizons traveled outward. Most of those years, the spacecraft was in hibernation mode. The cruise was a long act of waiting. Pluto was reclassified as a dwarf planet by the International Astronomical Union on August 24, 2006, 8 months after New Horizons launched. The team had been working on a mission to a planet. They arrived at a dwarf planet. The mission's importance did not change. On July 14, 2015, after 9.5 years of cruise, New Horizons made its closest approach to Pluto. Closest approach was at 12,500 kilometers above Pluto's surface, at a relative velocity of about 49,600 kilometers per hour. The flyby lasted hours. The downlink rate from Pluto, given the distance of about 6 billion kilometers, was only about 1 to 2 kilobits per second. Most of the data the spacecraft collected during the flyby could not be transmitted back to Earth in real time. It had to be stored on the spacecraft's onboard memory and trickled back to Earth over the following months. That morning, at the Johns Hopkins Applied Physics Laboratory, the team gathered in the control room. The geometry of the flyby meant that during closest approach, the spacecraft would be pointed entirely at Pluto, using every available watt to operate its instruments. It would not be transmitting to Earth. For several hours, there would be no signal from New Horizons at all. The wait was excruciating. Alan Stern, who had been working on the idea of a Pluto mission for almost 3 decades, was in the control room with most of the team. They watched the clock. They watched the dish status indicators. There was nothing they could do during the silent phase. They waited. The carrier signal came back at the predicted time. The Doppler shift was within the expected range. The spacecraft had survived the flyby. The first telemetry packets confirmed that all instruments had operated nominally, all data had been stored, and the spacecraft was healthy. The team broke down in the control room. There were tears. There were embraces. There was applause that went on for many minutes. Alan Stern said that morning, "We are now on the other side of the world." Pluto had been imaged for the first time in human history. The images, over the following days and weeks, were astonishing. Pluto was not the dead frozen ball the textbooks of the 1980s had described. It was a world of stunning geological complexity, mountains of water ice rising kilometers above the surrounding plains. An enormous heart-shaped plain of nitrogen ice named Tumbao Regio for Clyde Tombaugh, who discovered Pluto in 1930, that appeared to be convecting like a slow lava lamp. Possible cryovolcanoes, fields of dunes made of frozen methane particles. The surface was geologically active. Pluto, the dwarf planet at the edge of the solar system, was alive in the geological sense. Charon, Pluto's largest moon, was also a surprise. Half the size of Pluto, it had been expected to be a featureless icy ball. The images revealed a giant tectonic canyon running across its face, multiple distinct terrains, a North Pole stained dark red by organic compounds that had probably condensed from Pluto's atmospheric haze and migrated to the cold pole over geological time. The data returned from the flyby took more than a year. By late 2016, most of the New Horizons data had reached Earth and been processed. The team continued operating the spacecraft. In 2019, on January 1st, New Horizons made a second flyby, Arrokoth, an object in the Kuiper Belt, about 1 billion kilometers beyond Pluto. Arrokoth turned out to be a contact binary, 2 lobes touching, a frozen relic of the early solar system that had never been disturbed by another world. It is the most distant solar system body ever visited up close by a spacecraft. New Horizons is still operating. It is in the Kuiper Belt, on a trajectory that will take it eventually out of the solar system, beyond the heliopause, into interstellar space. The probe is small. The signal is faint. The team monitors it from APL. There is no Mars-class flagship mission to Pluto on any timeline anyone is currently planning. The next time a spacecraft enters orbit around Pluto, or makes a close flyby of any object beyond Neptune, will be many decades from now, if ever. That is the Pluto story. A planet that took longer to authorize a mission to than to fly the mission itself. A target that was cancelled and resurrected over almost 30 years. A spacecraft the size of a piano, costing about as much as a moderate office building, that did what no flagship mission could afford to do. The smallest probe ever sent to the outer solar system, against the longest odds, completed its mission. The phrase to remember, the one that I introduced earlier and that you have been hearing in different keys, the route is the only route. For Pluto, the route was a launch window that opened in 2006 and closed in 2007, with a Jupiter gravity assist that would not repeat for many years afterward. If New Horizons had not made that window, Pluto would have been deferred again, possibly indefinitely. The route was the only route. The team that found it and flew it deserves more credit than they have received. And now there is one more planet to talk about, or rather, not a planet at all, but a star. Because the lessons of this entire video, the slowly accumulating realization that close is not easy, take their final and most extreme form when we look beyond the solar system at the place that is, by far, the closest thing outside our own backyard. Part 11. Proxima Centauri and the Wall at the Edge. Proxima Centauri is a small red dwarf star, about 1/8 the mass of our Sun, sitting just over 4 light-years away in the southern constellation Centaurus. It is the closest known star to the Sun. It is part of the Alpha Centauri system, a triple-star arrangement that includes Alpha Centauri A and Alpha Centauri B, both Sun-like stars, and Proxima itself, which orbits the pair at a distance of about 13,000 astronomical units. Proxima has at least 2 confirmed planets, including Proxima Centauri b, an Earth-mass world orbiting in the star's habitable zone. The discovery of Proxima b in 2016 made the closest star to the Sun into one of the most interesting targets for future exploration in all of astronomy. There may be a habitable, possibly even inhabited, world 4 light-years away. 4 light-years. The number sounds small. 4 years, at the speed of light. Light, after all, crosses the diameter of the Earth in a tiny fraction of a second. Light from the Sun takes about 8 minutes to reach Earth. Light from Pluto, at the time of the New Horizons flyby, took about 4.5 hours to reach Earth. 4 years sounds, when you say it casually, like a manageable journey. You could spend 4 years doing many things in your life. But we do not travel at the speed of light. The fastest object humans have ever launched is Voyager 1. Voyager 1 is currently moving away from the Sun at about 17 kilometers per second. That is fast enough to circle the Earth in about 40 minutes. Fast enough to cross the United States in about 3.5 minutes. But at 17 kilometers per second, the distance to Proxima Centauri, about 40.2 trillion kilometers, would take Voyager 1 approximately 76,000 years to cover. 76,000 years. If Voyager 1 had been launched at the dawn of human civilization, it would still not have arrived. And Voyager 1 is not even aimed at Proxima Centauri. It is on a trajectory that takes it past a different star called Gliese 445 in about 40,000 years at a distance of about 1.5 light-years. It will pass Gliese 445 and continue. Nothing in the foreseeable future will bring Voyager 1 anywhere near our nearest stellar neighbor. To reach Proxima Centauri within a single human lifetime, we would need to travel at speeds approaching a significant fraction of the speed of light. To travel at 1% of light speed, about 3,000 kilometers per second, we would still need over 400 years to cover the distance. To travel at 10% of light speed, about 40 years. The faster, the better. But the faster, the more expensive in energy, and the energy curve goes against us very fast. To accelerate a spacecraft to 1% of the speed of light using conventional chemical rockets, the kind that fly Falcon 9 and Atlas V and Saturn V would require, by the math of the rocket equation, about 10 to the 26th kilograms of fuel for every kilogram of spacecraft, 10 to the 26th. That number is roughly 100 times the mass of the entire Earth. A spacecraft going to Proxima Centauri at 1% of the speed of light on chemical propulsion would weigh more than the planet we live on. The math does not work. It does not even pretend to work. So chemical propulsion is out. Every concept for interstellar travel that has ever been seriously studied uses something else. Ion propulsion, nuclear thermal propulsion, nuclear pulse, propulsion of the kind imagined in the Orion project of the 1960s, detonating nuclear devices behind a heavy pusher plate to propel the spacecraft forward, solar sails driven by sunlight pressure, laser sails, driven by enormous laser arrays in Earth orbit, shining their beams at lightweight reflectors, carrying microscopic payloads. Each of these has its own challenges. The original Orion project, designed to use fission bombs as a propulsion source, has problems both with the engineering and with the political reality of detonating hundreds of nuclear devices in Earth's atmosphere. An interstellar version of Orion, using fusion devices, would require something like 400,000 tons of spacecraft mass and a pusher plate 100 meters in diameter, and would still take roughly 150 years to reach Proxima Centauri. The most promising current concept for an interstellar mission within this century is called Breakthrough Starshot. The idea, advanced by the late Stephen Hawking, the physicist R.V. Loeb, and the philanthropist Yuri Milner, is to build very small probes, gram-scale spacecraft, each one essentially a postage stamp-sized chip with a tiny sail attached, and accelerate them to about 15 to 20% of the speed of light, using a 100 gigawatt array of lasers on the first. Ground. At 15% of light speed, the probes would reach Proxima Centauri in about 20 to 30 years from launch, and then take another 4 years for the data to return to Earth at the speed of light. The mission concept is technically conceivable. The engineering is staggering. The cost would be measured in billions of dollars and decades of development. The project has not been substantially funded. As of a recent report, the program had not progressed past early concept studies. If we ever do send a probe to Proxima Centauri, it will be small. It will be fast in the sense of relativistic mechanics. It will not be crude. It will not slow down at the destination. It will fly past Proxima Centauri b at 15% of the speed of light, take whatever images and measurements it can in the brief window of close approach, and continue out into interstellar space forever. The first close-range data on a habitable planet outside our solar system, if we ever obtain it, will come from a flyby, by exactly the same logic that drove New Horizons to fly by Pluto rather than orbit it. The smaller and faster the probe, the more achievable the mission. There is something to feel about this, slowly, before we close. Every difficulty we have walked through in this video, planet by planet, takes its most extreme form here. The Sun's gravity well became Mercury's barrier. Distance became Mars's barrier. Radiation became Jupiter's barrier. The institutional commitment of holding a team together for years became Saturn's barrier. The sunlight problem and the communication delay became the ice giant's barrier. The patience of a small probe became Pluto's barrier. At Proxima Centauri, all of these become walls higher than anything our engineering knows how to climb. Distance, scaled to 4 light-years, becomes a journey of decades at the absolute physical limit of what current propulsion can imagine. Energy, scaled to 1% of light speed, becomes a planetary mass fuel budget for any conventional propulsion. Time, scaled to the round trip including data return, becomes longer than a single career, longer than many marriages, longer than the working lifetime of any one team. Sunlight, at 4 light-years, is meaningless. The probe will see no help from any star until it arrives at the destination star. Communication, at 4 light-years, takes 4 years one way. There is no real-time anything. The probe is on its own. And yet, and this is the gentle inversion I want to leave you with before the final part, and yet, the solar system in this light is small. The planets we have walked through, in all their difficulty, are next door. Mercury is 48 million miles away at its closest. Pluto is 6 billion. Proxima Centauri is 40 trillion. The walls that kept Mercury unvisited for 30 years, and the walls that have kept Uranus and Neptune unvisited for 40 years, become, in the cosmic perspective, the walls of a small, intimate place. The solar system is the only thing we can ever reach. The walls that surround it are not just engineering challenges. They are walls of physical law, the speed of light, and the rocket equation, and the exponential cost of energy, and the finite duration of human institutions. The hardest planets to reach are also the only planets we can ever reach. That is the deepest emotional anchor of this story, and it deserves to be felt, slowly, on the way to the closing. The universe has built around us a small backyard that we have just barely learned how to walk through. Every planet in that backyard has its own particular difficulty. Together, those difficulties are not despair, they are the texture of our home. The solar system was not designed to be visited. It has, nevertheless, allowed us to visit it slowly, expensively, cleverly, decade after decade. And what lies beyond it, while not forbidden, is far enough that for the present we are tied to the small place we have. Maybe that will change. Maybe a breakthrough Starshot kind of mission will fly. Maybe future propulsion technologies will shorten the 4 light-year journey. Maybe not. The truthful answer, tonight, is that we do not know. What we do know is the solar system. We have begun to know it. And the small, gentle thing we have learned, the one we have learned by walking from Mercury outward, planet by planet, through every variable that the universe uses to keep us at a distance, is that knowing it at all is a thing that one species, with one set of patient cleverness, can do. Part 12. We have not explored the solar system, we have visited it. Pull all of it together, slowly, before we close. We started with a small inversion. The closest planet to Earth is Venus, but the second closest is Mercury, and Mercury is harder to reach than planets 100 times farther away. The reason was the Sun's gravity well, the realization that close in distance and close in delta V are different things, and that one particular planet, in the wrong corner of the gravity field, can become unreachable for 30 years simply because the math of getting there does not allow the rockets we have to deliver enough fuel to slow down. We watched one trajectory designer, Chen Wan-yen, at the Jet Propulsion Laboratory in 1985, sit down with the problem and find a route nobody had seen before. We watched Messenger fly that route 7 years, 4.9 billion miles, 6 gravity assists, an eccentric orbit designed to let the spacecraft cool between close passes of a planet that reflects sunlight like a mirror. And finally, on March 11th, 2011, become the first spacecraft to orbit Mercury. We watched the discovery, over 4 years of mapping, that the planet closest to the Sun has water ice in permanently shadowed polar craters. The most counterintuitive single piece of geometry the solar system has shown us. We watched the spacecraft die by deliberate impact on April 30th, 2015, fuel exhausted, mission complete. We walked outward. Mars, where distance for the first time really is the dominant constraint, and where the cost of distance is not measured in miles but in fuel mass, in 2.5 years of human confinement, in the radiation dose that accumulates across the cruise, in the impossibility of resupply, in the 10 Saturn V class launches required to assemble a single mission. The hardness of Mars is the hardness of weaving every variable together and finding that they all push the same way. Mars is not impossible. Mars is the planet whose difficulty has exhausted every other system we have ever built. Jupiter, where energy to fly to was modest, but where orbital capture and radiation became the dominant difficulties. Galileo's heroic and damaged mission, the high-gain antenna that never opened, the atmospheric probe that lasted 57.6 minutes before being crushed, the deliberate impact in 2003 to keep Earth biology away from Europa. Juno, threading the polar gap between the radiation belts, still operating, still measuring, still mapping the inside of a planet that is mostly liquid hydrogen. Saturn, where the difficulties added a new variable, the institutional commitment of holding a flagship team together for 7 years of cruise and 13 years of operations. Cassini-Huygens, the great mission, the only landing on a body in the outer solar system, the grand finale dives, the methane lakes of Titan, the water geysers of Enceladus, the deliberate impact in 2017 to protect the moons. Uranus and Neptune, where the variables we had been learning, distance, sunlight, communication latency, mission duration combined to push entire flagship missions off every decadal study and into a kind of indefinite future. The ice giants are where we stop. They have been visited once each by Voyager 2 in 1986 and 1989. We know almost nothing about them up close, compared to what we know about Mars or Jupiter or Saturn. We have not gone back. Pluto, the smallest probe, the longest deferral, the patient route, 3 decades of cancelled missions, replaced finally by New Horizons in 2006, arrival in 2015, flyby hours long, data return more than a year. A planet, or a dwarf planet, by the time the spacecraft arrived, turned into a real world of mountains and nitrogen plains and possible cryovolcanism. A mission that proved, again, that the route is the only route, and that finding the route is what unlocks the planet. And Proxima Centauri, the wall at the edge of the solar system, where every variable we have walked through tonight becomes enormous, where the closest star outside our system is 4 light-years away, and a Voyager-class probe would need 76,000 years to arrive, where even the most ambitious gram-scale interstellar concept would take decades and might never be funded. The wall at the edge is not really a wall. It is the realization that the solar system is the only place we can fully reach, and that, having reached it, we have done something extraordinary by any reasonable measure. Here is the reframe I want to leave you with, the one that has been quietly building under everything else. We have not explored the solar system, we have visited it. The difference is everything. Exploration implies completeness, a thorough walking through, a knowing. We do not know the solar system. We have visited 8 planets, 2 of them only by flyby, and one of those flybys was 40 years ago, and one was 37 years ago. We have landed on a handful of moons. We have driven rovers across a small fraction of one planet's surface. We have mapped, in detail, the surfaces of perhaps 4 or 5 worlds out of the dozens that have surfaces worth mapping. We have measured the deep interiors of 2 or 3 worlds. We have characterized the atmospheres of fewer than that. The solar system is, in every meaningful sense, mostly unstudied. We have visited it. We have not explored it. And the hardest planets to reach are in many cases not the planets we have reached. The planets whose moons we have not yet landed on are arguably harder to reach than the planets themselves. Europa, Enceladus, Titan, Triton, Ganymede, Callisto, each of these may host a subsurface ocean, may have prebiotic or possibly biotic chemistry, may be the most interesting place in the solar system after Earth. We have flown by them. We have not gone down into them. To go down into them, we will need missions that combine every difficulty we have walked through tonight, plus a new one. The difficulty of penetrating an ice crust kilometers thick to reach the water beneath. That is the work that lies ahead. The solar system, in all its small contained way, is not finished. It is barely begun. Settle into that, slowly, before the closing. The sun is up there, the bright point in our sky, surrounded by a small backyard of planets and moons and asteroids and comets and ice and rock and a few patches of permanent shadow where, against every expectation, water ice has been hiding for 4 billion years. We have walked some of that backyard. We have not walked most of it. The solar system was not designed to be visited. It has, nevertheless, allowed us to visit it. The fact that we have visited it at all is the most demanding piece of cleverness humans have ever produced. Every photograph of every planet you have ever seen exists because someone, somewhere, found a route that nobody else had seen. Every line of data, every measurement of a magnetic field, every characterization of an atmosphere, every chemical analysis of a moon's surface, every one of these things exists because, somewhere in the chain that produced it, a person at a desk solved a problem that the previous generation had thought unsolvable. Chen Wan-yen found Mercury's route. Gary Flandreau found the Grand Tour alignment. Alan Stern kept the Pluto mission alive through 3 decades of cancellations. Thousands of people whose names I have not said tonight, and whose names you may never hear, sat in offices and laboratories and control rooms and turned the universe's no into a small, careful, expensive yes. That is what the solar system has been for us. Not a thing we conquered, not a thing we crossed. A thing we visited, slowly, with great difficulty, one route at a time, by the patient ingenuity of people who refused to accept that close was the same as easy. Close is not easy. The route is the only route. The solar system was not designed to be visited, and yet we have visited it. Hold those 3 thoughts together, gently, as you drift. Mercury is still there, with its polar ice. Mars is still there, with its dust storms and its frozen seas. Jupiter is still spinning. Saturn is still wearing its rings. Uranus is finishing one of its 42-year polar seasons. Neptune is throwing its impossible winds across an atmosphere that has not been visited in more than a generation. Triton is breathing nitrogen plumes into the dark. Pluto is moving slowly outward, away from the sun, with its heart-shaped plain of nitrogen ice still convecting at a rate too slow for human eyes to ever see. We have begun to know all of this. We are nowhere near finished. The next century, if it happens, will bring missions to places we have not yet touched. The next century, if it does not happen, will leave the planet standing where they have always stood, waiting patiently for any visitor patient enough to find the route. The solar system will wait. It has been waiting for a long time. It can wait longer. Good night.